All right, we can get started now that it's 7:30 for our little honors session here. Let's get on down here. There we are for the no class meeting day. And so what we're going to be talking about is the sample size calculations. And in fact, let's just take a little quick look here. Now this was the homework we were working on last time. And what we'd like to do is we'll revisit number 2, because if you recall, when we did that confidence interval, it was pretty wide. And you probably wouldn't be very happy with having a confidence interval that wide. And so what are you going to do about it? Well, you're going to increase the sample size. But you say, well, how big do I need to increase it? Well, that's what we're going to learn about now. But here's the traditional sequence of events. First, if someone's made a claim, that's the first thing we'll do. We'll test the claim. But for heaven's sake, don't stop there. Follow it up with a confidence interval. And when you're doing it with technology, that's so darn easy to do. So not only does the confidence interval, reaffirm the conclusion of the hypothesis test, but it gives you more information. It lets you know how narrowed down you have things, and that the width of your interval is what I mean by narrowed down. And if that's not narrowed down, well, you're well aware of it because you look at that wide interval and you say, I really need that to be narrower if I'm going to have a good idea what this population proportion is. And the idea is you say, what would make me happy? If the margin of error, that's half the width, were this small, and you will state how small you want that margin of error to be. And you also will state how high a confidence level you want. Maybe you want higher 95%. Maybe you're a little persnickety and you want 98%. Well, we can calculate what that'll cost us in terms of how big of a sample size. So let's get over here. Now this is the guide. This is like the nice shortened version of the lecture notes. But let's take a look at the lecture notes to see why this works and that where these formulas come from that we are using. Let me make this a little bigger so everybody won't have to squint to read the text. Now the margin of error, now just remember that is half of the width of our confidence interval. That's that distance, that equal distance we go above and below our statistic, either sample mean or sample proportion, to create our confidence interval. Another reason we did the hand calculation so you could really see that. Well, and also we learned with sampling distributions, and we also did the hand calculations, so it would hopefully reinforce that that's where the interval came from. The width of the interval was determined by the sampling distribution. And you can see, those sampling distributions can sure look different in their spread depending on the sample size that was used. The larger the sample size, the more scrunched in the sampling distribution is. Okay. Now, so there's the formula for the margin of error E. You'll recognize this was that distance we went above and below our sample mean to get our confidence interval. You recall that from our hand calculation days. Well, just like in many different areas of study, we come across formulas, things that the human race has discovered these relationships, and they can embody them in a formula where each letter or symbol represents something. And so that's what this is. But quite often, in the many different fields, I know comes up all the time in the sciences and also in business, these formulas, and you need to rewrite them. See, this one is solved for E. That means E is all by itself on one side of the equal sign. Well, sometimes you want to use algebra to rewrite these so it's solved for a different symbol. And that's what we'd want to do with this one. Instead of solving it for E, we say, let's solve it for N. In other words, If we were given the margin of error E, and we were given the standard deviation of the population, now what we always use for this is just an estimate of it. We'll take the sample standard deviation from a large sample, and that'll be a good estimate of this. And of course, the Z is determined by the confidence level you're using. And as you recall, that was the most of the work in doing the confidence interval by hand. But the idea is that you would be given these three things, and based on those, you could calculate what your sample size needs to be. We just got to use the algebra, but that's okay. That's a prerequisite for this class. You could use algebra to solve that for n, and if you did, you'd end up with this formula. So we got three different sample size formulas, and I want to make sure you don't think that they magically appeared out of nowhere. That no, they're just rewritten formulas that we have for our margin of error E, that equal distance we went above and below our statistic to create our confidence intervals. All right, so hey, you know what we ought to do? Something I wanted to suggest, because I've got the schedule all figured out here for quite a bit, that oh, I guess we don't need that there anymore. That was just a little filler there. But let's look at this document here. It wouldn't be a bad idea for us to be looking at that, and we could use it to review what we've covered so far, and at the same time we get a little peek at what we haven't covered yet, just to build up a little anticipation. So if I open that one up, so let's look at what we have. Let's make this bigger. Well, that's bigger. I want to make sure you can see it okay. So now how will you recognize which statistical method is needed? Because we've covered some statistical methods, and we're going to cover some more. And I want you to kind of notice how we figure it out. So of course, your first question is always, what are they asking for? So here's some things we have and have not covered yet, but will shortly. Now, we definitely have covered this. This is what you were doing on exam number 2, when they're asking you to calculate the probability, say, of one randomly selected from the population. Of course, you've seen where more than one is randomly sampled, and they ask you the probability of the sample mean being an interval. That was a couple homeworks ago. Also, they could ask you to find the interval that contains the middle, 76% of the population. And you would use inverse norm to do that. Stuff you've done. And of course, hypothesis test confidence intervals that you were doing the last homework using the functions on your calculator. Of course, you saw that flow chart. And this is what we're going to cover today, the sample size. And here's the little flow chart for it right here. See, these are the three formulas, and they're on your formula sheet. You don't need to memorize them. But it shows you the questions you ask yourself. And there's not very many questions, just one or two. So first of all, the first thing that you're being asked is, what are they asking for? And you identify they're asking you how large of a sample would be needed, and then they make their demands. But so notice that when you do the homework for Friday, how different they look from anything else you've seen before. They're asking you how big of a sample size would be needed. And you say, well, now that I know it's a sample size calculation, I got it narrowed down to 3 possibilities here. Let's ask another question or two and find out which one it is. The second question you always ask, you'll notice, is what type of data is it? Is it the numerical quantitative data? In other words, is it all about the population mean? That goes over here, and that's this formula. Or is it categorical data? And thus, it's all about the population proportion. Well, follow this arrow. Oh, you got one more question, and then you'll know which formula to use. This one's a pretty easy one to answer. Do you have a p-hat, a sample proportion? They sometimes call it a prior estimate of the population proportion. Hey, either you do or you don't. If you do, use the formula that has the p-hat in it. And if you don't, use the one without the p-hat. It's as simple as that. But what you've got to do with each time that you practice in the homework, practice asking these questions. In fact, every single exercise you do, practice asking these questions. Why? Because that is how you're training your brain for what it has to do on the exam. And of course, in your future career, you're going to look at a situation and be able to recognize, oh, I need this statistical technique for this situation. You know, that's one of the most valuable skills you could be getting from this class. But you got to practice it in order for that to develop. All right. And so now linear regression, we won't get to that till after exam 3. So that'll be one of the last things we cover. But what are they asking for? So these are the sort of things that you've seen or going to see. Second question, what type of data is it? We only have these 2. Now, so far, to answer this question, how many random samples were taken? We've only done 1. But next week, we're going to be looking at where 2 samples are taken, because we're going to be comparing 2 populations with each other. So just know that this question is coming up. In fact, when you're reviewing for Monday's class, you're going to be looking at one of these scenarios where there's 2 samples. So it's nice to see this now. Now, let's suppose that if it were the quantitative data and 2 samples, then you got one more question to ask. And this is what you'll start working with, you know, after this session, after you've done the homework for Friday and you're reading the material for Monday. It's going to be talking about, what does it mean to have matched pairs where my 2 samples are matched and paired up with each other? Because either they are matched or paired up or they're not. So once again, we'll be working with that next week. And of course, if it's 2 samples and not quantitative data, it'll be categorical data, and that's this technique. So stuff for next week. You got this little flow chart here that what we're doing today. Oh, and here's this little flow chart that this is what you were doing in the last homework, so that you knew which statistical method to use on your calculator. So that's a handy flow chart. Why, you know, this might be a handy thing to have printed out and pinned up somewhere and just keep reviewing. Now, this is going way back when you were trying to keep straight the difference between a population distribution, sampling distribution. And this summarizes the shape, center, and spread for these 3 different distributions, and all 3 of those can be transformed into the standard normal. So all helpful stuff to keep reviewing and running through your head every day between now and the final exam. And that gives you plenty of time for it to sink in. But just very helpful little summaries that have been created for you, how to keep everything all organized. All right, so what we're gonna do here, here's your formula sheet that you're gonna get for exam 3. And let me shrink it down so you can see there's the 3 formulas. Now, when you look at these, and you should probably have this printed out and by your side at all times, that let's look at what all 3 have in common. Do you notice all 3 of them have this little Z with a funny asterisk after it? That represents the critical value. Now, if you recall, back when we did confidence intervals by hand, and you found that critical value, that's when you would put the confidence level. That was the area in the middle of that Z distribution, and you found that Z score that was the right upper bound. Well, that's what this is. Now, rather than make you have to do that sketch every time, you've got this little table. But I just want you to remember where this table came from. In fact, let's just refresh your little memory. Now, let's suppose that we had a 90% confidence level. So let me get my little annotation tool up here. Whoops. Oh, I was wondering what's going on. Got my little pad here that I write on upside down, and that was why everything was acting weird. So I'm going to use my little tool here, and let's suppose we're going to do a, what do you say, 98%. Well, this is 95, so I just know it's somewhere out here. So I'll just draw a little line there, and I'll draw a little line here. Oh, I better have it draw the straight lines. And then I'll shade that in. So what I'm doing is, this is what you won't have to do because you have this table. But I want to make sure that you know what this table is representing. So I've got that. And of course, I need to clearly label here that this area right here, and then what that area is, and then what that area is. Whoops, I didn't go over far enough over here. I meant to go over here. All right. Whoops, I don't want to use an arrow. Let me get my little eraser. There we go. I meant to go right there. So let's shade that in. And this little arrow. All right, so what we always did was we said, now if this is going to be 98, I subtract that from 1, divide by 2, I get 2%. I subtract from 1, I get 2%. Then half is over here, so I'd have 1% over here, and I'd have 1% over here. Now this is the Z distribution. Remember how we would find this critical value right here. They said, oh yeah, we used inverse norm. And then we took the area to the left. 98% plus 1% is 99%. And then 0 and 1. And if we punch that into our calculator and round it to the 4th decimal place, you know what we got? 2.3263. And you can punch that on your calculator, reassure yourself. Okay. So rather than make you do this every time to get your critical value for your sample size calculation, you can just look it up at the table here. Okay, but all I ask is that when you look at the table, you realize, oh yeah, that's saving me from doing all of this work that I used to do all the time. So let me clear my drawings, and let's scoot this back on up. And so what I'll do is, we'll get some practice here, maybe look at a scenario, use the correct formula, but what you're going to find is all you're doing with these formulas is just plugging in the numbers and calculating it. Because, you know, you get your critical value from here. The other values are just given to you in the actual question, the exercise, the scenario. So why don't we do this? Let's go and let's look at homework 14. I'll shrink that down, don't need it that big. And going back to number 2. Oh, I'm going to resize this and get my calculator over here. Oh, there it is. Let's see if it's that on. Is it working? No. Sometimes if I leave this on too long, I have to start it up again. There we go. Let's hit the clear key. Now, let's just go ahead and put this into our calculator. So we'll press Stat, go over to Calc. Now notice that this was the categorical data. Now, for part A, you did one prop Z test. Then when you did the confidence interval, you did one prop Z int. Now let's see. So X, that was the 191. That was the count of how many were in the category of interest. And 500 was the sample size. And they told us to do a 95% confidence interval. Isn't it amazing that's all we have to do? Just enter in the date info from our sample, the confidence level, highlight, calculate, hit enter. But look how wide this is. You know, that's approximately from 34% to 42.5%. That doesn't sound very narrowed down to you, does it? In fact, let's actually see, what would that margin of error be? Well, let's look at the distance between the lower bound and upper bound. So all we got to do is punch in the upper bound, 424, and subtract the lower bound. Won't that tell us the distance? 941, did I punch it in? Yep. So that has a width of a little over 8.5%. That's a pretty wide interval. You probably don't feel like you really got a good idea what that population proportion is. Now, half of that is our margin of error. So let's just divide that by 2. So essentially what we're doing here is we're taking our sample proportion, which is the 191 divided by 500, and we're going above and below this distance, 4.259% above and below to create the interval. Well, let's suppose that we're going to make our demands here. So what I'm going to do is, better make a note here. All right. So I'm going to work on the formula sheet here, because that way I got some room here to do my work. So let's get my little annotation tool. Let's see, maybe I'll do blue ink this time. Okay, now here's the deal. Our margin of error was over 4%. So wouldn't you be a lot happier if the margin of error E is only 2%? Wow, that's, just half. It's a little less than half. Can't complain about that. And so the confidence level, hey, why don't we up that? It was 95%. But let's now make our confidence level, oh, what the heck? Let's make it 97%. So we're raising the confidence level and shrinking the margin of error. So you notice that one thing is being made bigger or larger, one thing is being made smaller, but they're both making the confidence interval better. Because a better confidence interval is with a high confidence level and a very narrow interval. So think of these two as our demands. Okay. Now the question is, if you recall the flow chart, the next question, if it's categorical data, which it is, it can't be this formula because that's only for the numerical quantitative data. So it's between these two. So do I have a p-hat or not? Well, remember we did because we had we just did a confidence interval. And you've already done a confidence interval, you always have a p-hat. So don't forget you have it. That was our x over n. In fact, we entered that into the calculator when we did the confidence interval. So that was the 191 out of the 500. Oh, and if you punch that into your calculator, in fact, let me just do that over here. 500. Okay, so that might be easier. Rather than writing a fraction, I can just put in that decimal. So this is 0.382. All right, so looky here. We know which formula to use. It's got to be this one. And if someone were to ask, are you sure that's the right one? You could say, well, of course I'm sure. Can't be this one because that's for the quantitative numerical data. And meaning it's between these two. And how you decide between these two is whether or not you got a p hat. And I got a p hat, so I'm using the one with a p hat. And that's all there is to it. So now with these sample size formulas, you've got to always show your work. So first thing you want to do is write out your formula, then underneath it, substitute the numbers in. Now, you can put that little asterisk there if you want to, or if you leave it out, that's fine too. I don't care. So I'll show it without it, just so you know it's perfectly okay not to have that there. It's just a notation that our textbook uses. Now, have I got all these numbers? Sure I do. I got my p hat right there. I got my e right there. And I'm going to look up this z right in this table. All I got to do is plug in my numbers. All right, so let's put in our p hat, 382. And once again, you're expected to show this work that I'm showing you. And then we'll do a 1 minus 0.382. And a parenthesis, put that there. Now let's look up this critical value. Now, if our confidence level is 90%, what will this be? Well, let's see. That would be 2.1701. That's easy, just looking it up. But when I look it up, I should remind myself what that means. If I put this area in the center, shaded that in, figured out what's in the tails, and found that z-score for that upper bound, that's what this is. Because that tells me if I go this many standard errors above and below the center, I'll contain the middle 97% of all the sample proportions. Okay, now we got to put in the margin of error E. Now, what have you heard me tell you about whenever you're given a value as a percentage? Is there something I need to do to this before I ever put it into a function on my calculator or into a formula? Hopefully you remember that if I'm given it as a percentage, I have to write it as a decimal. And if you have trouble with that, then just go to your calculator. Remember that whatever they gave you as a percentage, divide it by 100, and that's what it looks like in decimal. Because remember, that's what a percentage is. It means this out of 100. So I got that. I can make sure that I get the decimal point in the correct place. Because if you don't get in the correct place, it'll really mess up your answer. So now this only happens with the categorical data. You have to worry about that with a margin of error. Sometimes they give to you as a decimal. Sometimes they give to you as a percentage. Just remember, they give to you as a percentage. Put it in decimal. But when you show all this work, you've demonstrated you know the correct formula and you know the correct values to put in. Now, let's make sure you got the calculator skills to put this into your calculator correctly. Now, notice the parentheses I have here. They're very important because you see these parentheses right here ensure that only this part gets squared. You don't want to square the whole thing because you'll get the wrong answer. So let's just go ahead and put this into the calculator. Let me move this closer here so you can see it. And Maybe I'll get rid of this little line here. We don't need that there now. So we'll punch in the 0.382. I'll do the left parenthesis. That's important. 1, subtract 0.382. Right parenthesis. That parenthesis is important. Now a left parenthesis. 2.1701. Hit the divide key, and we're divided by 0.02, right parenthesis, and then hit the x squared key. So you want to make sure, because, sometimes it takes people some practice, but this is why it's so critical that you write it out first, because let's suppose you did everything written out correctly, but then you had it equal to the wrong answer. All that means is you don't have the calculator skills yet. So keep working on it till you do have the calculator skill. Watch those parentheses. And once you got that, hit enter. And let's jot this answer down and talk about what it means. Think about what it means. So I go over here, and n is this 2779.4. I'll stop there. So what this is saying is your sample size has to be at least this big. It's got to be this big or bigger in order to meet these demands. Now, what were my demands? Okay, so this is a demand. We're demanding that the margin of error be this small. We're also demanding this confidence level, that it be this high. This is very demanding. This is what making the sample size so big, because these are so demanding. And once you got that, then my sample size has to be at least this big or bigger. Okay. And because it has to be that big or bigger, we always, we don't round off, we round up to the next whole number. So I don't round off to 2,779. Nope, I round up to the next whole number, which is 2,780. So that's my final answer. I don't leave my answer with a decimal part on it. That's silly. That's not a sample size. A whole counting number is a sample size. And now this is the only place we round up. Everywhere else we round off. But with sample size calculations, it's customary to round up to the next whole number. So just think, wow, before we just had a sample size of 500. How does this look compared to a sample size of 500? It's a lot bigger. Yeah, but look what happens if you get a sample size this big. So now if you were to go out, get a sample size of 2,780, gather the data. Of course, you go through that and count how many are in your category of interest. That would be your X. And use that, once again, in one prob z int, and construct yourself a 97% confidence interval. Lo and behold, believe it or not, your margin of error will end up being that small. You say, now how does it know that? Because we know the pattern that these sample proportions will take on in the long run. That we know how closely those sample proportions cluster around the population proportion they're estimating. So that's the idea. So you're saying, well, don't feel too bad that, you took this prior random sample of 500. It was not a complete waste, because at least you had a p-hat to use, which is better than not having one. So that leads us to the next question. Well, what's so bad about not having a p-hat? Well, let's take a look. Let's move that aside. We could say, well, let's suppose, what if I didn't have a p hat? Well, let's see what the calculation would have been like. Okay. So this would be, what if we had no p hat? In other words, this prior sample had never been taken, and I know nothing about this population of categorical data. I only know two things, and the two things are what I want to know. All I know is I want a margin of error E this small, confidence level that high, and I don't know anything else. These are the only two things I know. Well, you're going to have to use this formula because that's all you got. Well, you can't use this one because that's for quantitative numerical data. You can't use this one. You got no p hat. You're stuck with this one, buddy. So make the best of it. So you say, okay, this is all I got. Now you might be thinking, hey, I kind of like this. Look how much simpler it is. Well, how simple the hand calculation is really isn't a consideration. There's more important considerations that we'll be talking about here. And of course, so that'll be the z and the e. That'll be squared. 0.25. Of course, the z, it's 97%. So just like before, you looked it up here. That's the 2.1701. Oops, let's put that down there. And the margin of error E is the 2%, which you're going to enter in decimal. And don't forget to square it. So let's go ahead and calculate that. Let's see what we get. Let's hit the clear key. We'll do 0.25, a left parenthesis, and that left parenthesis is very important. 2.1701. Like that, and divide by the 0.02, right parenthesis, and then the squared. Now it's very important because that only this part is supposed to be squared, not the whole thing, and so the parentheses make sure that that happens. And so let's jot this down and talk about its result. So that equals 2,943.3. Now, of course, what we're going to do is we're going to round up. So my final answer is 2,944. So that's how big my sample size will need to be. And you say, hey, that's bigger than this one over here. Yes, it is. Let's see, how much bigger is that? So we got 2,944, and the smaller one was 2,780. So you're having to sample an extra 164. And so you say, now, well, what's the deal? What's the difference between these two really? And why is this 0.25? That's what you really want to know, isn't it? Isn't that bugging you just a little bit? I bet it is. Okay, well, I can explain that. Let me get my little annotation pen here. Let's get a little different color here. Oh, I'll do green. Now, remember what the population distribution looks like for categorical data? It's just a bar chart. So let's just do a little bar here, over here, and let's go up here, over, and then, whoops, and then down. And let's suppose the other category. So you just got these two bars. Now let's suppose the height of the smaller bar The small bar represents the population proportion. So that's why I put P here. So that's my population proportion, the proportion of the category I'm interested in, and the other category is way up here. Now, do you think you would need a very large sample size in order to figure out that this category is bigger than that category? Or do you think you'd figure that out pretty fast? Yeah, you're probably pretty fast. So now let's consider another scenario. Let's go over here, there. So there's your population proportion. And here's the other category. And so your population proportion is the height of this one. And now the question is, how big of a sample size do you think you'll need to take before you can figure out this category is bigger than that one? And you're basing it just on a random sample. So do you feel like you're going to need a much bigger sample size to figure out there's a difference between the height of these two bars than over here between these two? You say, yeah, I mean, I need a lot bigger sample size to figure that out. Over here, I could figure that out pretty easy. I wouldn't need nearly as big a sample size. All right. So once you're clear that this is like the worst case scenario where I would need the largest sample size to figure stuff out, well, what is this height that we're at here? So what you're seeing is that we're around, or the closer we are to 0.5, the harder it is to tell the difference. You see, if 0.5 is here, look how far away we are from 0.5, the p hat is. But if your p, or your sample proportion, is close to 0.5, it's the worst case scenario, and you really need a large sample size. So if that were the case, let's look at this one with the p hats. All this over here says is this is the worst case scenario of that. You say, are you sure? Well, yeah. So imagine this. What if that were 0.5? Okay. And of course, this would be 0.5. Okay, so 0.5 minus 1 is 0.5. So essentially, we got 0.5 times 0.5. Now, I ask you, what is 0.5 or 1/2 times 0.5 or 1/2? 0.25. That's why you got the 0.25 there. Right here. That's just what this would be equal to in the worst case scenario. So that's why this is bigger. It's the worst case scenario. It's saying, look, if you don't have a p hat, an estimate of the population proportion, we'll have to assume the worst and use this formula. Now, you might be getting a way bigger sample size than you need, but that's how it is when you're doing the worst case scenario. So next time, get yourself a p hat if you don't want to deal with this. So that's why it's so nice to have a p hat, because you know you're not doing a lot of extraneous extra work with a larger sample size than what you need. Because, you know, sample sizes cost time and money. You don't want to be getting a larger one than you actually need to meet the demands. Because if these are just the demands you need to meet, then you want to meet or possibly exceed, which is where we just round up to a whole number. But you may not want to exceed by this much, as that would be too expensive. All right. Okay, so let's go ahead here and clear all of this out. And let's look at another one. And so what I'm going to look at here is I want to go over here to the lecture notes. Well, there's a little comic to help you remember increasing the sample size does two things. Well, and the sample size is so big and so strong, it can scrunch in the interval. So that just reminds you, helps your brain remember, oh yeah, increasing the sample size shrinks the interval. And also because it's so big and strong, it can lift up or raise the confidence level. So it's just little memory tricks that make things easier to remember. Now the lecture notes are simply reminding you of how you used to find the critical value. You don't have to do this anymore. Remember, you've got the table to look up on the formula sheet. So what I want to do is let's get down here. There's your little flow chart again. I wanted to get to example 3. Let's look at this one. Suppose you want to know the average length of all fish in a huge lake. That would be great. Now, you don't want to do a census because then you'd have to catch every darn fish. But the idea is that you want to get a confidence interval where it's really narrowed down. So now you already took a random sample, but you weren't happy with the confidence interval. It was too wide, but it was not a complete waste because the sample size was large, at least 30, your sample standard deviation will be a good approximation of the population standard deviation. So that's great because you're going to need that. But I want you to notice these key words here is when they ask, how large of a sample? See, you've never been asked that before, have you? No, they're not asking you to construct or find a confidence interval. They're not asking you to test a claim or choose between two ideas. They're not asking you to calculate a probability. No, this is completely different from all the other scenarios you've done. So that's just great. Makes it easy for you to identify and tell these different techniques apart from each other. So once you realize it's a sample size calculation, you go, oh, well, that narrows it down to 3 formulas. Then you ask yourself what type of data it is. And you say, well, I'm measuring these fish. That's quantitative data. Well, great. There's only one sample size formula for quantitative data. It's the one that has the standard deviation in it. So now you know that. And let's see here. Let's make a note that, okay, so we got the formula right here. Oh, and then of course you'll be able, they want a 99% confidence level. You'll be able to look that up on that little table. It's and that critical value just happens to be 2.5758, but you would look that up. I'm going to work right here because I got all the information I need. But it's important for you to remember that I'm using this confidence level to get that critical value. So I'm going to, so I know that this is equal to left parenthesis and Z. So I'd look that up on the table. And I find where 99% is the last one in the table, and that critical value is 2.5758. And that's going to be multiplied by, I'll do a little asterisk because that's what it looks like when I do multiplication on the calculator. And our population standard deviation is being estimated with this approximate value of 2.75. And it's being divided by the margin of error E. Now, we're in quantitative data, so this will be in whatever units you're measuring, which is 0.75. So remember, you don't have to worry about converting to decimal because we're not dealing with percentages here. This is inches, so don't go messing with it. And then, of course, that's squared. All right, so there's our work. All we got to do is enter that into our calculator. So let me move my calculator in closer. There we go. Let's clear things. Now, left parenthesis. Got to put the whole thing in parentheses. 2.5758 is our critical value times, see that little asterisk, then 2.75, and then divide by our 0.75, right parenthesis, and then the square. And if you've got that, hit enter. And so let's write that down. So 89.2, of course, we round up to 90. So if we were to go and get a sample size of 90 and use that to construct a 99% confidence interval for the population mean, lo and behold, that margin of error E actually will only be 3/4 of an inch. So if I go 3/4 of an inch above and 3/4 of an inch below, why, that'll be 1.5 inches. Boy, the interval will only be 1.5 inches wide. And if you feel that's narrowed down enough, well, that's why you ask for that small of margin of error. Do you notice a difference in the size of our samples between the quantitative data versus that categorical data we were just working with? Do you notice how much smaller the quantitative data sample sizes are? Keep that in mind when you're actually doing an experiment and research in real life. If you are lucky enough to be working with quantitative data, your sample sizes don't have to be nearly as large. But sometimes it's more work because these are measurements. Sometimes the measuring can be tedious. Whereas with the categorical data, you're just sorting, throwing these into two piles, which can go faster. But still, there's a huge difference in the sample sizes. Now let's talk about a few things that can go wrong on the calculator. You know, these are all common mistakes we all make when we're first learning. I'm going to press the second enter key to call in the last thing I just did. Here's a common mistake, forgetting to square it. Now, if I forgot to square it, that's my answer. Now, do you think you're going to have a sample size of 10 in any of your calculations? No. You see, our sample sizes that were initially did in our initial problems were large enough for the conditions to be met, but they were not large enough to get things narrowed down enough. So we don't just have large samples, we got really large samples. We got big samples. So it'd be ridiculous for you to think that you're going to have a small sample size like that. You should know something is terribly wrong if you get a sample size like that. So look back at your work and see if you can catch your error. You know, just like you do with those practice exercises that you try and solve for yourself, and if your answer doesn't match with what it shows, you try and find the error. Well, that's what you're doing here. So what did I do wrong? And I think this is pretty simple. It's not very complicated. You probably should be able to see that. Oh, I forgot to square. Of course. Now, we could, by the way, when we were doing the ones, see, you don't still have it here. So I'm going to enter. Remember when we were working with the categorical data there? Here's the formula we did. We had the 0.382. That was our p hat we had. And then we had 1 minus the p hat, which was the 0.382. And then we had that multiplied by, and our critical value on that one that we did was 2.1701, and it was divided by 2%. Now, 2% is 0.02. But what if, instead of doing that, you had put a 2 in there? And then, of course, you did the squared. So everything is correct, except you put in 2 instead of 0.02. what will your answer look like? Does that even look remotely possible for a sample size calculation? Or do you know you obviously did something terribly wrong? So anytime you forget to, if it's given to you, your margin of error is given to you as a percentage because it's categorical data, and you don't put in decimal format, your answers won't make sense. So if your answers don't make sense, look back at your work and find your error. And hopefully you would catch that. You say, oh, that's what I did. So you go back in there, put in the 0.02, right parenthesis squared. And then, now we're talking. Now that makes sense. It's really big because it's categorical data. Now, here's another mistake. Let's go back to where you forgot to square it. So you could see that, oh, I had done everything right, but I forgot to square it. And once again, looking at your answer, it should be obvious you did something wrong. So basically, I did the same error that I showed with this one. I forgot to square it. And once again, it should be obvious. For categorical data, this would be ridiculously small. So you realize, oh, I forgot to square it. Watch out for this mistake. Well, then I'll square it now. I'll square my last answer. Now, is squaring this really what you want to do? You'll be squaring the whole thing, and you're not supposed to do that. You're only supposed to square this part. So if you did that, you're going to get the wrong answer. So you're not going to have this correct answer. You're going to have this incorrect answer. Now, unfortunately, this answer isn't as obviously wrong as the others were. So you'd be less likely to catch an error like this. So the whole point of where I'm showing you of all the things that can go wrong is this is why we insist, and we won't even give you credit unless you show your work. And that's for your own good, because it's too easy to make a mistake on your calculator and get the wrong answer. But if we can see this being shown, we can give you the partial credit you deserve because you know what you're doing. You just got to work on your calculator skills. All right. Well, that really is the extent. We've done all three types that you're going to see. Here, let's clear this out. And so you got the homework handed out to you last time. And if you misplaced it, you can get another copy from Moodle. It's up there. And so notice this, they're asking you, how large of a sample is needed? Okay, how large of a sample is needed? Do you see it? Hopefully, how many cars should be in the sample? So really notice that. Really notice how different these questions are from everything else. And up here at the top, just a remind, show your work for the hand calculations. 0 points if you don't show your work. Also, pretend someone asks you, now why are you rounding up for? You're supposed to round off, aren't you? Why are you rounding up? And you'll just explain to them, because our answer is telling us our sample size needs to be at least this big. And at least means that big or bigger. And that's why it's customary to round up. So we meet or exceed the demands. And what are those demands? How small the margin of error is and how high the confidence level is. All right. Well, anyways, the lecture notes, it has some worked out examples there for you, so you can always study those. And I think you're at the point where you can handle this homework now. I will say this, that in number 3, they're going to have you do a couple sample size calculations, one where the margin of error is 1,000 miles, and then do it again where it's only half as much. So they cut the margin of error by a half. Okay. And so then they ask, now what effect does doubling the required accuracy. Now, doubling required accuracy means you're cutting the margin of error in half. You're shrinking the interval by a half. Now, how much bigger sample size do you need? What's the ratio? Well, no problem. Just compare your answers to these two questions. Compare those two sample sizes, and that'll tell you. Now, you're going to have to think about this. So you'll just have to see if you can figure that out before we meet on Monday. But that's your challenge question. Why is that the expected result? See if you can figure that out. Even with the mathy explanation. No, you might be able to, but that'll be your little challenge. All right. Of course, these two questions cover some concepts we talked about earlier, so hopefully you'll be okay on that. All right. Well, that definitely covers this stuff. Oh, and Melissa, Catherine, of course, feel free to ask if you have any questions. That's where you click on the little chat thing and type in any questions. And I should hear a little beep. And I should have mentioned that at the beginning, so you know that you're always welcome to ask questions at any time during a presentation. But I just started yakking and forgot about that. Oh, hey, let's go back. So if anyone has any questions, you can type them on in. But definitely, get this document, how to recognize which statistical method to use, and just start practicing it and reviewing it every day, what we've covered so far. And then just look with curiosity what we haven't covered yet, and knowing you will get to learn that. And the nice thing is, you don't have to do any messy hand calculations. It's so easy. You'll just be shown what function to use on your calculator. And you're just going to be reusing the same concepts you've already learned about hypothesis tests and confidence intervals. In other words, this class gets easier now that you've paid your dues and have covered the foundation of the fundamentals of hypothesis tests and confidence intervals. So that now when we show you a new statistical method, you don't got too much more to learn. It's just a little bit more, and you know another statistical technique. So that's why if you're still happen to be rusty on any of the earlier stuff, all those concepts on exam number 2, not the hand calculation, but the concepts you need to know. And you're covered. Well, let's see. Well, that does cover everything. So you get that, and let's see. So where are we here? Right there. So you'll be ready for the meeting on 2. And of course, you'll be reading about, two dependent samples. That's where you have 2 samples and they're matched and paired up. But just, read that over and just sort of get your head wrapped around it a little bit. So that way, when I go over it on Monday, it's not all brand new to you. All right. Okay, well, that covers it for this session. And so we'll see you Monday. Oh, and just so you know, the link for this, I'm going to have it posted right here. And I'll probably make it the first thing. But, I've got to transcode it, and then I got to upload it, and then I'll post the link. So it'll be there by tomorrow morning or late tonight. One or the other. It'll be there. All right? So we'll see you on Monday.